So first, I would like to make a remark concerning this theorem of Schur, which we had yesterday. So the situation was that we had some map from X, Y, further, so it's smooth, torus vibration. It has essentially that's the reason. I argue that the canonical bundle of White-Hilda is ample, and first discuss the case where it's not left, but as Frederick observed, it's much easier because what S is isomorphic to White-Hilda. So this implies, of course, that omega White-Hilda is left. I mean, we have since, of course, we have the cotangent like this. So this is left. So then this is right to right? So the cotangent bundle of White-Hilda is ample. Now it's first of all it's F, but then this Kawamata argument shows that it's ample actually, and then it's also it follows that also that the cotangent bundle of White-Hilda is F. So so this question. So the canonical bundle of White-Hilda is ample. And the cotangent bundle is F. So can we conclude, under which conditions can we conclude that omega White-Hilda is actually big? So omega White-Hilda is big. Of course, if and only if you project device, and then this is big, and this, but we also know that this is Nef. But Nef, if you have a Nef line bundle, then it's big, if and only if the top germ class, it's to the power what? 2n minus 1 is positive. So it's always non-negative. And this is something which is called the nth secret class of White-Hilda. Depends a little bit on the definition of the secret class. If you look at everything is strange because it takes the that's not hyperplanes but lines, and then you mix up by
the first equivalence is in definition for locally free shift to the peak. So I think we didn't define this bigness for actually locally free shift.
I mean, the vector bundle is big if and only if the O of 1 is big. That's
okay.
It's the definition. Right?
The definition. Okay, and then, of course, I mean, the question is, are there any, suppose the canonical bundle is ample. Let's say then White-Hilda is true. So then the question is, are there, is it possible to have surface or give examples if existing surfaces? Yeah, let's say White-Hilda canonical bundle. It's ample, omega White-Hilda is Nef, and C1 squared is C2. So you always know C1 squared is at least C2, and bigness means the second class is positive. This means C1 squared minus C2 is positive, but of course it could happen that C1 squared is C2. So,
For example.
Do you know any example of that?
In that line.
No. canonical bundle should be ample. What was your?
Theta rimasto in an abelian triple. This is how this is G equal
Okay.
3, K square equals 6.
Okay.
There are no rational counts, so the example. I don't know if the cotangent is generated, is globally generated.
This is okay, yes.
I don't know if it's NEF. I think it's globally.
No, if it's globally generated, no, it's NEF. Everything is, yeah, okay. So you have examples. Okay. So this is possible. But the cotangent bundle, yeah, okay. So anyway, so you have a clear criterion here in this situation when it's big or not. Okay, and then I wanted to comment on this theorem of erase everything. This theorem Iwai Matsumoto. Okay. Iwai. So the assumption was so X is a projective manifold, and the canonical bundle is NEF. And then we have the following assertions: second term plus 0, we can only if omega x is NEF, and the numerical dimension is 0 or 1. And B was if omega x is NEF, and the numerical dimension is 0 or 1, then kx is 0. And then Höring's theorem applies. Okay, so maybe I give some indication on the proof. So this we already checked yesterday. And this was, yeah. So the other way, so we know by Miyaoka that the cotangent sheaf is generically NEF. And the second calculus is 0 by assumption. So then the claim is this implies that the cotangent is NEF actually. And actually this has nothing to do with the cotangent bundle. This is actually a statement for reflexive sheaves. And you need only, you don't need the full generic NEFness, you just need generically NEF with respect to some fixed ample devices. Yeah, and I mean, the reason is basically the following. Say that omega x is semi-state. And then we have a Chern class inequality, C1 squared times h to the power n minus 2 is less or equal to times the2 of x n minus 2. So this is this Bogomolov-Giesinger inequality. And then, but this is 0. So then it follows that C1 squared times h n minus 2 is 0. And since kx is left, it follows that C1 squared actually is 0. Okay, so you have here equality in this inequality, and this has a lot of consequences. There's a very strong consequence. So this implies that omega x is projectively flat. Which means that's given by a representation in PGLL. But I mean, what we need is that omega x twisted with minus kx divided by n. So the normalization, so to speak, this is numerically flat. This means that, I mean, if you don't like these Q sheaves, you can also say that it takes the symmetric power and tensor it by minus k. So we have a vector bundle which is numerically flat, which means that it is left and the dual is also left. Yeah? But then, of course, I mean, what can we say? Yeah, I mean, this is in particular, this is Neff. This sheaf, the dual of this sheaf is Neff, because the canonical is Neff. Yeah, it's minus Neff. So if you twist something, yeah, omega x is of course then this one here twisted by kx divided by n. So this implies in particular that omega x is Neff. And then, yeah, okay. So I made the assumption that the cotangent bundle is semi-stable. So if it's not semi-stable, then we have the Haber-Narasimhan filter. So in principle, you can reduce it to lower dimensional cases. Yeah? And then, of course, one has to, this requires some, yeah, but it's just technical, but no real. Okay. Then the next is Neff. What? Ah, yeah. Okay, we still have to prove this one here. Because I mean, there's an argument by Zhao and Hu. Cotangent bundle is Neff. They prove that there is a line bundle when one subcase here such that the numerical dimension of L is the same as the numerical dimension of. Now, so this is also some kind of Haber-Narasimhan argument. Yeah. Oh no, I don't have to say this. So the first translation of L is the same as the first translation of K. Yeah. And now, I mean, but we know that the numerical dimension is one, yeah? So if the numerical dimension of x would at least be 2, then we get then it follows, of course, that the numerical dimension of R would be at least 2. So we have a subsheaf in omega 1 with numerical dimension 2, and this contradicts this Bogomolov-Sommese vanishing. The numerical dimension must be, can only be 1. Okay, so this is basically what's going on here. And then for the second statement, yeah. So now we are in the situation where the numerical dimension is 0 and 1. And in the first step, one proves that X is not special in the sense of Campana, using this L. And the second step then is the following. So if it is not special, then we have this core map, Campana, from X to Y. I think you will explain this, right?
Yes.
Okay.
Tomorrow.
And then, yeah, maybe I agree a little bit. I mean, so this is basically holomorphic for purposes. Well, it's almost holomorphic, but it's already also. Anyway, we have nice fibers. The general fiber is special and has omega f net, of course. And we have that the Kodaira dimension of X is the Kodaira dimension of F plus dimension of Y. This is also a property of the coin. And then the numerical dimension of F is at most 1, of course. So then by induction, yeah, Kf is semi-out. Yeah. So and then, yeah, we conclude. We conclude that the numerical dimension of X is say if the numerical dimension is 0, anyway it's clear. So this is larger or equal to the canonical of X. So this is the canonical of F plus the dimension of Y. So this, of course, is at least the dimension of Y. And this is 1. So you see that the numerical dimension of X is the same as the Kodaira dimension of X. But then by Kawamata, we know that we have Kawamata. If you have equality here, Kawamata says Kx is 0. So that's roughly the argument. So you prove that it's non-special. This requires some different. I mean, this is not completely clear. Yeah, you have to work here. And then the core map analyzing the core map gives by induction gives the expandings. Okay, I think I will not go further into details here. But this, of course, for the cotangent, for left cotangent bundle would be an interesting problem. In that case, I mean, yeah. Okay. So now coming to lecture 2. So the subject of lecture 2 is the following non-vanishing conjecture . Okay. So this is follows. X is a projective manifold. And you assume that the cotangent bundle is pseudo-effective. I will explain this in 1 second. Then there should exist some n such that But some symmetric power should have the same. So that's what we would like to explain. Okay. So what's the definition? Something wrong?
That's reminds me some emblem.
No. Hmm? Okay, I will give some explanation. Yeah? So the definition is if you have a locally free sheaf E or some reflexive sheaf or coherent sheaf, then E is pseudo-effective. If and only if the line bundle is pseudo-effective. So this means that first Chern class of this, let me attenuate by theta. The first Chern class is in the closure of the effective cone. Okay, so there's an equivalent definition. This is probably what you mean. So equivalent is the following: fix some H amp. E is pseudo-effective if the following holds. For any positive number C, there is some K in N, such that for all I in N, with I larger than C times K, you have sections in SIE tensor OX of K. So it's not necessarily the case that E itself has a section, but if you tensor a little bit, some symmetric power, then you get sections. Yeah, so pseudo-effective is, so to speak, the limit of effective. Yeah, but I mean, if you think of line bundles, it sits on the boundary of the effective cone. But I mean, the effective cone is the cone generated by the classes of the closure of the cone generated by effective divisors. But of course, I mean, in general, you cannot expect that on the boundary also you have effective divisors, but you just have limits of effective divisors. And these limits are called pseudo-effective for line bundles. I mean, if you look into literature, for instance, Matsumura or these people, they have a different notation of pseudo-effectivity. They also assume something on the non-Neff locus that it does not project, it should project on the base. So this was the original definition which I gave with Desmaillies and Schneider some long time ago, but then we realized that it's not a good definition. So the good definition is this one. Yeah, because
you need to tensorwise stairs. In the case of omega x pseudo-effective implies
no.
it's a
conjecture.
Ah, okay, it's not
Not a definition. The definition is here. Okay, of course, the non-vanishing conjecture, the traditional non-vanishing conjecture for the canonical says, of course, that if Kx is purely effective, then there exists some number n such that Ox of mkx is a such. Yeah, so for the canonical, it should happen that although the canonical is on the boundary of the effective cone, it should still be effective. Yeah, so this is, so to speak, very unique for the canonical bundle. For the anti-canonical bundle, it's already false. Okay. And of course, if you like, you can also, instead of take omega 1 x, to take omega q, and if q is n, then you land in the traditional non-vanishing conjecture.
Examples for the canonical bundle? What are examples to this for the canonical bundle? You say it is false for them.
Yes, I think there are some examples, but that's. Yes.
But the conjecture for Kx should be easier than which one? Which one? The bottom one should be easier, no? The conjecture.
Yes.
Yes. For Kx.
Should be easier.
Which one?
It's a line bundle.
Yes, this is unclear to me.
The bottom conjecture. The top conjecture.
Yes.
It should be easier than the top.
Which one is easier, this one or this one? Well, I mean, I will discuss the case of surfaces, and even for surfaces, this conjecture is still open. So, I mean, from this perspective, you may say that this conjecture is more difficult.
More difficult.
Yeah.
Yeah, exactly. Okay. I mean, Kx behaves well, and upstairs things are much more delicate.
Yeah.
Venus skilled and the formation. No. I like that. Check on top.
I mean, some other remark is that I also think, and in principle, I'm also in minimal models, but then you have to take into account similarities. So just a remark that we have a singular word for X, say KLT or canonical singularities or whatever you want. Yeah. And then, of course, omega 1 X has to be replaced by a sheaf of reflexive differentials. I mean, there's always a sheaf of Kähler differentials, but this can be, of course, very singular in general. And then you take the bidual, and this is the reflective piece. And still, you can make sense to speak of pseudo-effectivity because you can take the projectivization in the O1. And of course, I mean, this the traditional non-vanishing conjecture is, of course, if for KSE non-singularities, yeah. I mean, in framework of movie theory, you always deal with singular versions. Okay. But I mean, since it's already difficult in the smooth case, I will completely neglect this case. And maybe another remark is that this condition here can be replaced also as follows. So this is equivalent to saying that there exists some finite eta cover. Such that you have a holomorphic cover. Yeah, and so this is usually called the augmented regularity. Qt is, so to speak, the maximum of all regularities of all finite eta covers. So that's, yeah, not so difficult to see. So before I state the main theorem, maybe I skip. Yeah, very short. So there are some easy properties of pseudo-effectivity. So if you have a birational morphism of two projective varieties, then omega 2 of x is pseudo-effective different from if omega x is effective. So this means it's a birational property of the existence of this conjecture up here is a birational property between smooth projective varieties. So that's, yeah, I leave this in exercise. I mean, that's not difficult. Some other proposition maybe, if you have a finite surjective thing, for smooth, so if omega x is pseudo-effective, then omega x with twiddle is also pseudo-effective. And converse is, of course, false in general. If F is defined. Okay, so this is easy to prove. So now the theorem I want to discuss, this is joint work with Andreas Höring, is the following. 2.8. Oh. It assumes minimal projective surface. And I assume that the Kodaira dimension is 1. So, of course, omega x is pseudo-effective. And I mean, we have a minimal projective surface with Kodaira dimension 1, so we have an elliptic vibration. given by the multiple of the canonical. We have an elliptic vibration. So if F is not isotrivial, then the non-vanishing conjecture holds. Okay, let me, before I start the proof, maybe I missed some remarks. I mean, the non-vanishing conjecture to one is of course true if the Kodaira dimension is minus infinity or zero. Yeah, you look at the list and then, yeah. I mean, for instance, if it's minus infinity, you have a P2 or P1 bundle over a curve. And if the curve is P1, it cannot be pseudo-effective. And if the curve is has at least genus 1, of course, then it's clear that you have holomorphic forms. Yeah? And of course, for K3 surfaces and torus also. Okay. The case Kodaira dimension 2 is completely okay. Of course, if omega x is big, then it's clear. But if it is not big, I think we have, at the moment, we have no idea what to do. No, so, I mean, okay, if P1 is clear, it's larger than P, but in the other cases, I don't know. I should say at this point, well, maybe I state this as form. This is also a result theory. If the dimension of X is anything, and if the canonical bundle is numerically trivial, Kodaira dimension 0, so to speak, then if omega x, so yesterday I started discussing the case where omega x is nef. And then we saw that the second Chern class is 0, and then there was a finite eta cover, which is a torus. But this can be generalized in the following way. So if omega x is purely effective, then there is a finite eta cover such that X pure is a torus. But I will not explain anything on this result. Yeah? And of course, this implies that the irregularity Q tilde is 0, and then you have a finite, and you have you get symmetric differentials here on X. There's another interesting thing. So if you have a projective manifold, you assume that the fundamental thing is infinite. So then there's a conjecture by Eno saying that there must be some symmetric differential. If you have some information on the topology, yeah, I mean, it looks quite reasonable. I think this is known. If you have a representation, a linear representation. In shear elements. With infinite image. So this is a theorem by Greenbaum. Luminosity total. Okay. So these are the remarks, and now I want to discuss the proof of theorem 28. Yeah, the non-isotrivial case, well, maybe it's also solved by now. The isotrivial case. No? I think the proof will be divided in two parts, one today and the next tomorrow. Because here I really want to discuss some details. So the first point is that we may assume that F is not almost smooth. So this means that not all singular fibers are multiples of elliptic curves. Namely, that if F is almost smooth, almost smooth means topologically you have just a smooth vibration, and then we know that the second current lasts. Yeah? And then, of course, the holomorphic Euler characteristic. This is C1 squared of x plus B2 of x divided by 12. C2 is 0, C1 squared is 0, so this is 0. And this implies that we have a holomorphic form. And there's nothing to prove. And of course, we may also assume that we cut that curve downstairs of P1. Yeah? Okay. So we erase everything. So set up is the following.
Sorry,
Yes?
may I suggest that you split the backbone in two so that you can erase just once a time, otherwise we are stuck to take notes. Thank you very much.
Okay, yeah.
Thank you very much.
Okay, okay, good. If I'm too quick, just complain, yeah? So, set up the following, I introduce the following divisor D. And you get a fiber. And then the fibers may have some non-reduced components. And I subtract, I look at the four fiber and then I subtract the reduced part. So this is a divisor which is supported on non-reduced fiber components. Then we obtain from the cotangent sequence, we obtain a sequence like this. I mean, in principle, we have a map from F upper star of the cotangent downstairs to the cotangent here. But of course, we have zeros along this. And the zeros in codimension 1, I subtract, so to speak. And then the rest is the ideal sheaf of some finite set. And then we have a relative polarizing sheaf. Yeah, I mean, if you compute term classes, you just see it. This where Z is a locally complete intersection. Or dimension T. So finite set.
How is that defined? How is that defined?
Z is, I mean, here you have a section here. I mean, you have the subsheaf, but the subsheaf, this is a line bundle. You have a section in omega x twisted minus this line bundle. So you have a rank 2 vector bundle, and the rank 2 vector bundle vanishes, the section of this rank 2 vector bundle vanishes on a finite set. Yeah, so this is this finite set. Yeah. We have if you have a rank 2 vector bundle on these, and you know that this, so this is, yeah, on the surface, so this is finite. And then there is a locally complete intersection of codimension 2. Yeah, because locally, of course, this is given by two holomorphic functions.
In fact, if you don't have homo, if F and G do not have homo components.
Yeah.
I mean, in fact,
Yes, sure. So if you have a section which doesn't have divisorial components,
yeah.
if you have divisorial components which are untwisted by the codimension one thing which I did here.
But the Z on the fibers are the points of where is it supported? Sure.
Yes, I mean,
Well,
yeah, that I'm not completely finished. So this is supported on singular points of reduced fibers, of reduction of fibers. Now, so you look at the singular fibers, you ignore multiplicities, and then you have finitely many points on every fiber, and this is that.
they can be multiple. I mean,
At the end, no, I think. But I don't care about that. So the final aim is so what we want in principle is that this sheaf here pseudo-effective. And it is good that from pseudo-effectivity we can conclude that this irregularity may develop in yeah, I mean, in principle, I mean, you are disturbed by the fact that B is P1, yeah, because you don't have holomorphic one forms on P1. But this is larger. So the hope is that it gets large enough to be pseudo-effective. And then from this pseudo-effectivity, you want to construct sections. So that's in principle what we want to do. Okay.
I don't understand notation that this so Z is supported on singular points of D. It's a point.
Yeah. So we have something fibers like this one. So we have a fiber could look like that, and then this is some of the bed points. Okay. So now I look at the projectilization of the projectile angle, and zeta will be O of 1. And y will be the projectilization of the ideal sheaf tensor omega x over d minus d. So, yeah, I have a quotient of this one, of omega x, by this coherent sheaf. And of course, if that is not empty, then this is not a locally free sheaf, but this doesn't matter. You can take the projectilization here, and this will be a sub-bundle, sub-variety of this one. Yeah, so you get it. So, and then you see easily that y is irreducible. And actually it is the blow up. The blow up of z in x. And the point is, of course, that, I mean, this is locally free. This is a complete intersection, locally complete intersection. So this implies in particular that this one is locally free of rank 2. It's a vector bundle, so to speak, vector bundle of rank 2 sitting on finitely many points. So this is important. If you blow this up, then you have a general formula, and then you see that y is really the blow up of that in x. Okay. So and then you obtain the following formula. The class of y in x is zeta minus the back the first term class of omega into 3. So this is a general blow-up formula. We will use it later. So and then I still have to introduce some notations. I look at K, E, so this is a finite set of points such that F upper star, the fiber over P is not a multiple and not reduced. So and then I decompose D in the following way. So these are the reductions, the Fi are the reductions of multiple fibers. And then I get the other part is sum B and K. And I call this D0. Whole thing is D0. So in other words, I decompose this divisor D in the part which coming from multiple fibers and the other. And then 2 star, B star, let me see, 3 star. Then 3 star is the so-called Zariski decomposition. Yeah, with the positive part is just the sum mi minus 1 Fi. So this means, in other words, that P is nef, this is clear, and the intersection matrix of D0, if you take all these components and you take the matrix, so this is negative definite or 0. And this is just to be computed. And P times D0D is 0 for all D. So this is easily checked. And then maybe this is the last thing which I'm doing today. So I remark the following. So I have the canonical bundle formula for F. So the canonical bundle formula says that the canonical bundle of X is the pullback of the canonical bundle of B. So this is related to what you said yesterday. But of course, you have something different, yeah? I mean, some additional stuff here. Namely, you can write it in the following way. That is the direct image here, tensor, and then you have its multiple fibers. So this implies that you get from 3 star, you get the following 4 star thing. That the canonical bundle of X over B minus D, if you compute this, is numerical equivalent to some multiple of F. So this is a general fiber minus D0. So this is a general fiber. And so the degree here of this thing is just the holomorphic Euler characteristic of OX. Okay. So I will stop here, and I think we should recall this equations, 1 star up to 4 star, and then tomorrow I will give the conclusion of the proof. But yeah, I think it would be too much today. I think I stop here.
So at some point, you said that if you have symmetric differentials, there is an eta cover with manifolds,
Yes.
but you have simply connected the manifold with the cotangent.
What did I say?
So you have another symmetric differential, but there is no eta cover.
I think it's the direction.
Exactly. It's not
One direction.
Did I say if and only if? Or
Yeah, I think
this is only one yes, there's one direction. If the irregularity is positive,
on an cover, then
You can construct this thing.
if you know this one, then you have an eta cover, and then you know that there exists some n such that H0 is n. Okay.
This is stronger.
Yes, so this is strong.
And so this is what you prove then.
Yes.
So you prove somehow something.
Maybe it's this one. Yes. Yeah. Okay. Okay. So it's simply connected. Yes. Although you prove this, what is that? This is, I think, this is an argument given by Anela. You have to upstairs. You have to, in principle, you have to cover a situation. Then you downstairs.
Okay.
And then you need some argument that if you averaging, that you don't get something which is zero.
Yeah.
So that's the point, so to speak. But this is a nice argument, I think.
Okay, thank you.
Yeah, okay. So this is the.
Questions? Well, if you can bring some.